Hello, so in this video we will be going over how to do shear and moment diagrams. So before we start off with the shear moment diagrams, there is some information that we need to know beforehand in order to solve these problems. So the first thing that we need to know is the equations of equilibrium. So we have to know these three equations of equilibrium. The first one is that if you sum the forces in the x direction, or the horizontal direction, then all the forces should equal to 0. And the second one is if you sum the forces in the y direction or the vertical direction, the sum of the forces must be equal to 0 as well. And lastly, if you sum the moments at a specific point, then it should also equal 0. The next thing that we need to know are the types of supports and their reactions. Here I will show three types of supports. The first one being the fixed support. So if there's a fixed support, then that means it will most likely show up like this, or it will be like a bunch of diagonal lines and will show that it is fixed at that specific point. So if it is fixed at that specific point, that means that that point is not going to be able to move in any direction or rotate, which means that we are going to have a reaction force in the vertical direction and a reaction force in the horizontal direction, as well as a moment at that point. The next support is a roller. Then this will be shown as a circle for the roller. So the roller can move these directions and it can also rotate. So that means that it cannot move up or down. So that means we will have only a vertical reaction. The last support that I will show here is a pin support. The pin support will most likely be shown as a triangle. The pin support does not allow this point to move up or down or in the horizontal direction, which means we will have a vertical reaction as well as a horizontal reaction. The next thing we need to know is the slope of different loads. So I have two examples here. One is for a point load and the other one is for the uniformly distributed load. So these are the support reactions and this is a load P. So if you have a point load, you will either just go up or down as shown here, and then since there is no loads here in this section, then that will remain constant and we will go down for this P load. So we go down here and then there's no load in this area, so we will be constant, and then for the support reaction at the end, it will go up, resulting to 0. And for the moment, since this is constant, that means we will calculate the area here and to find the maximum point here, and this will be linear. And as well as for this one, this will be negative, so it will go down to 0. And the maximum moment is here when it crosses from the positive to the negative shear. So as you can see, this is where it crosses it, and this is the maximum moment. For the uniformly distributed load, we have the support reactions here as well. And as mentioned before, for these, we will go up. And then for the uniformly distributed load, we will go linearly because this is constant. So then we will go linear. And then the support reaction is a point load, so we will go up again. Since this line is linear, then for the moment, that means that the line will be parabolic. So for this half, it will go this way, and then for this other half, it will go like this, resulting in a moment of 0. And in order to know what direction to do the moment, either this way, this way, this way, or this way, we can see that the area is decreasing as we move to the right. So that means that the slope must be decreasing. So here there's a higher slope, and then the slope is decreasing and reaching to 0 once we go to the right. So that means this is the correct form for the moment. And as well for this one, we can see that it is increasing. So that means we can see that the slope is increasing as we move to the right. So this is also correct. And for the other ones that are not going to be shown in this video are if there is a linear load like this here, then that means that the shear diagram will be parabolic and that the moment will be cubic. So in summary, we go from constant to linear to parabolic and to cubic. Then we will move on to the first example. So for the first example, we will draw the shear and moment diagram. So we see that it is fixed at A and there is no support at B, and there is a uniformly distributed load for 10 meters. The first thing we will do is to draw the reactions that we will need to solve for. So for the fixed support, as we mentioned before, there will be a vertical reaction we will call VA, a horizontal reaction we will call HA, and a moment that we will denote as MA. And there are no other supports, so it will only be these three reactions that we will be solving for. So the first thing we will do is we will sum the forces in the x direction, and we will say that to the left is positive and it will equal to 0. We can see that there are no horizontal reactions until we get to HA. So HA will be equal to 0. And then we will sum the forces in the y direction with the upwards being positive. And then, so we will see that we have the 20 of the uniformly distributed load. So we do 20 times the length, which is the 10 meters. This will be minus since it's going down. And then we have this other vertical reaction, so that will be plus VA, and it will equal to 0. And then we will solve for VA, and we get that VA is equal to 200. Now we will sum the moments from point A, and we will say that counterclockwise is positive. So then we say we have the MA here, and it is counterclockwise, so it will be MA. And then the other loads that we have is a uniform distributed load here, so we take the 20 times the 10 meters times the moment arm, which is 10 over 2. Since the distributed load, if we combine it, it will be halfway here as a point load. So then we take this distance here, which is 10 over 2 or 5. And that is the moment arm. And this will be negative. Since we see that it is going down, the uniformly distributed load is pointing down, and we are taking some of the moments from point A. So if we draw the arrow going towards this, and then you see that if you kind of combine these, you can get an arrow that is going clockwise. And since we denoted that counterclockwise is positive, then clockwise will be negative. And we set it equal to 0. And then we solve for MA, and we get 1000. And now we have solved for all three reactions that we were trying to solve for in order to draw the shear moment diagram. Now we will move on to draw the shear moment diagram. I'm going to draw these lines to help us draw these diagrams. So first, we are going to do the shear diagram. This will be the shear. This will be the moment. So the first thing we will do, we are going to start on the left-hand side. So we see that the first shear load will be this load here, the VA, and we solved for VA, and we saw that it was 200. So we will go up positive 200. So now we have the distributed load. So as we mentioned before, since this is constant, that means that it will go down linearly. So then we do 20 times the 10 meters, and it will be, that's 200. So then we are at 200, so we go down to 0. And that is all the shear that we include in the shear diagram. Now for the moment, we solve for moment A to be 1000, and we see that we denoted it as going counterclockwise. So that means that it will go down to 1000. We see that it is linear, so that means it will be parabolic. And as mentioned before, we see that it is decreasing in area. So that means that the slope of the parabolic curve that we're going to draw should have a decreasing slope as we move to the right. So we will choose to draw like this. And we reach to 0 because we draw the moment depending on the area of the shear. So we do 1/2 the base, which is 10 meters, then times the 200, this is the height, and we get 1000. So since we started off at negative 1000, and then we add it, so then we will reach to 0 moment, which is what we wanted to achieve. And those are the completed shear and moment diagrams for this problem. We will now move on to the second problem. So again, the first step that we want to take is to draw the reaction forces that we will need to solve for. So we have to look at the supports, and we see that this is pinned. So as we mentioned before in the video, for pinned, we will have a reaction in the vertical direction as well as a reaction in the horizontal direction. And for the roller, we mentioned before that it will only have a reaction in the vertical direction. We will denote VB. So we see that we have two unknowns in here and we have one unknown here. So to solve for one of the reactions, we will sum the moments where we have the most number of unknowns, which is at point A. So we are going to start off by summing the moments at point A. And again, we will say that counterclockwise is positive and it will equal to 0. We see that we have a distributed load for these 10 middle feet. So we will do, and then we can see that it will go down and then to point A, so then it will be clockwise. So then that means that it is negative since we denoted counterclockwise as positive, so that means clockwise will be negative. We'll do minus 2 times 10 times the moment arm, which is 10 over 2, plus the additional 10. So the point load will be here for the distributed load. So that means we take this length, which will be the 10 plus 10 over 2, which is the 15 feet. And then the other one that we have to add into the moment is this VB. So that one's going up and then this way, so that will be counterclockwise. So that means it is positive. So then we add it. We will do VB times the total moment arm, which is 30 feet. And it will be equal to 0. And then we solve for VB and we get VB is equal to 10. Then we can also do the sum of moments from the x direction for right is equal to positive. And we see that the only horizontal force is HA, so that means HA is equal to 0. And then lastly, we will do the sum of the forces in the y direction with up being positive and set it equal to 0. And then we will do VB, and it's positive because it's pointing upwards, minus the 2 times the 10 for the uniformly distributed load, minus because it's pointing downwards, plus VA is equal to 0. And we already saw for BV. So then you substitute the 10 for BB, and then you solve for VA, and you get 10 for VA. And from this, we can now draw the shear moment diagrams. This will be the shear, and this will be the moment. So we will start off with the VA here, and we solve VA is equal to 10, so we will go up 10. And then there is no loads here in this area, so that means that it will be constant until the 10 feet, and then until we hit the uniformly distributed load of 2. So then, since it is constant, that means that for the shear, it will be linear. So then we go down by, so it will be the 10 that we are originally at, minus the uniformly distributed load, which is the 2 times the 10 feet, and that will give us negative 10. So we are going to be down at 10, negative 10. And then once again, for this distance, there is also no loads, so it will be stay constant. And then we get to VB, and we saw VB is equal to 10, so then we go up 10. And I'm going to draw these additional lines just to make it clearer. I didn't draw this exactly proportional, but it's okay. And then we would move on to the moment diagram. So as mentioned before, the moment, to draw the moment diagram, we are going to calculate the area of these different sections here. So for this part, it will be 10 times the 10 feet, which is equal to 100. So the area of this is 100. So this is constant, so that means for the moment it will be linear. And so this is positive, so we will be going up linearly till we reach 100. And then for this area, it will be 1/2 the base, which is 10, and the height, which is 10, and that is equal to 25. And this also has an area of 25, which is negative, and it also has an area of 100, which will be negative. So since this line here is linear, that means that for the moment it will be parabolic. So once again we see that the area is decreasing as we move to the right. So that means that the slope has to be decreasing as we move to the right for when we draw the parabolic curve. So we can also just draw the different shapes for parabolic and see which ones will give us a slope that is decreasing as we move to the right. And we see that it is this section and this section. But since this is positive, this part is positive, shear, that means we will go with this one. A parabolic line until 125. We'll do parabolic until 125. Should be, it doesn't look, the drawing doesn't look exactly how it should, but gets the rough idea. So we will reach to 125 here. And then we will go down 25 because of the shear moment that we see in this area. And it will also be parabolic since this line is also linear, so that means that the line for the moment will be parabolic. And we see that the area is increasing, so we need the slope to be increasing as we move to the right. So we will draw it like this. Again, the drawing is not proportional, but it's roughly how it should look like. And then for the last one, we have the area of 100 from this area, so we will go down 100 to 0, since this was 100. And then 100 minus 100 equals to a 0 moment. And that is the shear moment diagram for this problem. And that is the end of this video. Thank you.